Started on time from now on. Because I know I keep telling people to come check me out at a certain time. I don't get here. And that's not good. Now, I'm not sure about this. All right, so let's see. Okay, brief intro. So if you never stopped by the stream before, this is the 39th episode of the Swift and SwiftUI Learnalong. So this is where you watch me, your host. Just call me Oat, brother. Just call me Oat. But you're watching me learn Swift in a very raw-like fashion, where I read this book, so you're not learning from me, you're learning with me, is the important distinction, and not in like a corny way. I mean, like, I'm actually learning this for the first time, and then we're going to do something with it. So I started a company and fully intend to build a application called MRP Panda. Already copyrighted, don't try it. Already got the domain, so you can't steal it. But the intention is that it's going to be an application for, well, in its namesake, MRP, so material resource planning. So effectively any customer out there, or any potential customer, what am I trying to say? My prospects, or anybody that is a user of an ERP system with a SQL backend and has physical inventory to manage effectively. And so that's the general consensus. We'll talk more about the app in general later on, but that's the idea of this stream. So we're learning it first, right? We're learning the thing. Then we're going to move into SwiftUI after this. So SwiftUI is a framework provided by Apple to write GUIs. So we're going to learn that, and then we're going to do some schema design, some API design for the eventual web server component of it. And then we'll hop back into another book, which will also be a Big Nerd Ranch Guide book on iOS programming. And so that'll cover the full gambit, the language itself, which is what we're doing now. Our GUI framework of choice. There's others, but we're going to roll with SwiftUI, and then we'll focus on the platforms themselves. So working with Apple's APIs. So that's what the other book will introduce. And then after that, we're just going to build the thing, and we'll probably do eventually either an Odin or maybe just like a raw C Learnalong 2, one of those. I'm not sure which one yet. Something like that. Maybe even V. Maybe. You never know. Yeah, that's the general idea. So stick around if that's cool. Otherwise, get the hell out. All right, so let's talk about yesterday. Yesterday was tough. We've been covering memory management, and so a lot of this it just opens up a lot of questions, like a lot of questions for me. And I've never been exposed to ARC, which is, we learned Swift's memory model. ARC being an acronym for automatic reference counting. And, generally speaking, we can, I don't know, it's probably too small to see, but let me make this bigger here. So every variable keeps its own reference count. So effectively anything that is referring to it or using it or might use it that still exists, it's keeping track of that count for each variable. And so the rule in terms of, because it's not garbage collection, so in terms of when it knows to go and remove certain things from memory is when this counter reaches 0. Which is good, right? It's pretty straightforward concept in that way. But what's not straightforward is some of the things they showed us yesterday. Or it wasn't straightforward to me. I shouldn't say it's not straightforward, but that's what we were learning about. And so they were just showing us different ways that we can guard against memory leaks in our programs. Chief among them was the Xcode tool. So the Xcode, this little button dilly. And so this will actually give you a graph of your code. And if you have memory leaks, it'll show you little warnings over here in the interface. So this is really cool. Really cool. I've yet to encounter. I mean, I've had minimal experience with other programming languages. Well, unless you count SQL. I wrote that for like 10 years. So, but that's different. You know, SQL is a programming language, but it's also a domain-specific language in a very specific way. Like, you know, it's to talk to databases. You're not writing general-purpose programs with SQL, at least not purely SQL. But anyway, after that, wrote some Golang for some, mostly microservice, lambdas, ETL jobs, data pipeline type stuff, but never a full-blown, user interface, the whole nine. So that's where I'm coming from, looking at all this stuff. So I try to relate it where I can, but otherwise, it's just been a bumpy ride. Chief of all this whole memory management thing. But to be fair, a lot of the stuff really doesn't. I mean, I like to understand it a little more deeply than the book provides. Not in like a Aristotle, I'm so smart kind of way, but just, I think it pays dividends to understand the underlying thing if the abstraction doesn't lend itself towards a good enough understanding, I guess. So, anyway, that's why I tend to dig sometimes, because some of the stuff, like the protocols, for example, like in Swift protocols, that all makes sense to me. It, of course, is an abstraction, but it's clear what it's doing, how it works, how it functions, and the why behind it. So I don't feel compelled to go like read the source code on how they're doing it under the hood. But for other things, I think it just kind of helps, especially with something as generic as memory management. So anyway, we went through that, looked at working with closures, working with reference types, and just how we can fight against those memory leaks. So we're going to move on because that beat the hell out of me. So where were we? We were on the very next chapter. Oh yeah, we're here. This is where we're here. Who's texting right now? Oh, okay. All right, for the more curious, a bit of history. Prior to the introduction of Swift in 2014, macOS and iOS applications were written in Objective-C, with some C and possibly even C++. Arc was introduced for Objective-C in 2011. I didn't know that. Prior to Arc, developers were responsible for manual reference counting, manually incrementing and decrementing the reference counts of class instances. Hell no, that's crazy. What? Seriously? Every class had an instance method to retain the instance. I'm sorry, I got the hiccups. Every class had an instance method. Oh. To retain the instance. Jeez. Can you imagine? Increment its reference count. And a method to release the instance, decrement its reference count. The rules for knowing when to retain and release an instance were relatively straightforward in theory, but easy to mess up in practice. As you can probably imagine, manual reference counting was a source of many bugs. If you retained an instance too many times, it would never get deallocated, causing a memory leak. And if you released an instance too many times... I'm looking at my mic bar right now. I used... Sorry to get sidetracked, but this is... Yeah, it's working perfectly. Hopefully it sounds good. It's this software that automatically just cuts out the background noise, like from the AC. So I hope it sounds good, because Well, first of all, I hope it sounds good because I already paid for a year, but I could get a refund, I'm pretty sure. But still, I mean, this is incredible. There's like nothing coming through. Anyway, okay, the rules for knowing when to, oh, wait, I read that. Imagine an instance method responsible for updating the value of a private stored property of a class. Manual reference counting code, if it could be written with Swift, might look something like this. All right, let's take a... Oh, I fucking hate this app. Pardon my French. All right. So, like, why do they maintain the whole... Like, you got page turn buttons. I can do left and right, but also if I hold... Like here, anywhere here, if I hold and drag, I'm getting text. But when I'm here... Sometimes I'm pulling the page. Like, what fucking sense does that make? Anyway. It's fucking 2024, brother. Markdown cell, code cell with the copy button. Fucking Kindle. Alright, so class, some class. Sorry, I got triggered for a sec. Right. There, so that's the code we're looking at. I don't think we're making a new playground, so it's going to have errors, but we're just looking at it. Okay, so class, some class. Let's break it down here, brother. So what do we know about class? We know it's a reference type, whereas structs and enums are value types. Reference types meaning when something else is using it, like if you assign an instance to it, like so, like simulation is a class. So when we assign this constant simulation to a instance of a class, it's not making a copy of these things. It just exists in memory once, and it just actually stores a reference, a pointer, which is this memory address. It just stores, or wait, maybe it's the reference. Oh no, that is it. Okay. It just stores a effectively a pointer to wherever these things are in memory. This object. And private. So private means it can't be accessed other than from within the same source code file. I believe that's what was intended, var being a mutable variable, not a constant. So if it needs to change, it needs to be var. Some object, in this case, we're using camel case for our variables, but notice our types have a camel case, or sorry, not camel case, Pascal case. If it were to have two sections, like a simulation type, like that, versus the camel case of the variables. But that's just convention. You can write it however you want. And then this is our type notation, the colon, some other class. So this is just saying that some object is, well, depending on what, this could either be a protocol, a type, or, no, that's about it, yeah. But we're saying it's of type, some instance like this. Oh, you know what? We shouldn't even be looking at that because this is pseudocode. They're saying this is what it would have looked like if... Okay, yeah, my bad. Throw all that out of your brain. Okay, we are happy to say that Swift's Arc feature not only takes care of this for you automatically, but also does so in an efficient way that increases the performance. Right, okay, my bad. I got totally sidetracked. Okay, I just wanted to look at how it was doing it. Yeah, so this is what similar to what they had to do before automatic reference counting. This is not something we as Swift devs have to worry about. Although we do still have to worry about memory to some degree, as we just learned. But yeah, so kind of like the C's free or malloc and dealloc or whatever the hell. But yeah, okay. So it used to be manual, now it's not, and that's a big help. We're happy to say that Swift's Arc feature not only takes care of this for you automatically, but also does so in an efficient way that increases the performance of your app. It does not just insert calls to methods like retain and release behind the scenes. Nothing like these methods actually exist in Swift. Instead, the compiler does reference counting work much more aggressively at a much lower level than your code. Oh, that's pretty cool, yeah. For the more curious, do I have the only reference? Unfortunately, Swift does not give you access to the actual reference count of any instances. Really? That's surprising. I guess if it's lower level than your code, that makes sense, because how do you write syntax for, for something like that? Although recall from chapter 18 that you can ask if a variable is the only reference to an instance via the isKnownUniquely referenced function. Okay, that does help. Yeah, actually, let me highlight that. If an item is even if you can ask an instance what its reference count was, the answer you got might not be what you expected. Throughout this chapter, we said things like, at this point, the reference count is 2. That was an innocent lie. Conceptually, it is perfectly reasonable and even helpful for you to think of reference counts the way we described. Under the hood, the compiler is free to insert additional changes to the reference count wherever it decides that your code can be optimized, as long as it does its job correctly. Yeah. See, isn't that crazy, though? I mean, if you imagine all the ceremony and all the effort you put into... I'm not saying this is a bad thing, because this is the case with most programming languages, but, the code that you write is all within the confines within, or defined by the backend, by the compiler. It's like the stuff that you write isn't actually what runs. It's the interpretation of what you write as implemented by somebody else. But that somebody else is likely, a lot, let's be real about it, within the programming sense, a lot smarter than you. So that's what I'm saying. It's not a bad thing, because that's the culmination of, tons of smart, inventive, creative, innovative engineer type shit. So just saying, it's pretty trippy when you think about it that way. There's so many layers to it. Anyway, as long as it does, but that's why it's also funny that's why it's funny when people conflate, software engineers with technicians, like the two worlds, like the traditional IT, not like the generic term, but actual, hardware guys, which kind of a dying breed, but you still have to understand hardware. But yeah, I always think that's kind of interesting. People just conflate the two, but they're worlds apart. You can be a great software developer and not really know shit about systems. I experienced that a lot in a past life. Anyway, let's see. Throughout this chapter, we said oh yeah. As long as it does its job correctly, there's no harm in your program. If you could ask what the actual reference count of an instance is, the answer would depend on what sort of analysis the compiler had done at that point. Additionally, there are some classes in Apple's system libraries that behave in strange ways when it comes to reference counting, the details of which are beyond the scope of this book. Okay, good. The important things for you to remember are how to recognize the potential for strong reference cycles and how to use weak to break them. Yeah, and that was effectively the... what is... Oh, I'm in the wrong file. Yeah. They're referring to this here, that keyword that we came across, so the weak var, so this makes it a weak reference instead of a strong one. Weak reference meaning it does not increment the reference count, therefore the compiler can help you out by looping over whatever the variable is, in this case container, and setting it to nil. That way those strong references that would cause memory leaks are now weak and do not cause memory leaks. Equatable, comparable, and hashable. So we finally got to the fabled chapter 25. This has been hyped throughout the whole book. We've read it at least 1,000,000 times. Chapter 25, you'll learn this. Chapter 25, it'll make sense. Chapter 25, it's all gonna click. All right, brother. I'm ready. You've spent a lot of time now learning to model data. You've explored value types and reference types and the free features that you can sometimes get from them. My back. Such as compiler synthesized empty initializers. Well, that's a mouthful. Compiler synthesized empty initializers. Okay. You have also seen useful behaviors that are enabled for when you conform to certain protocols from Swift standard library, like the swift.error, yep, or conforming to custom string convertible, yeah, that was useful. And implementing its required description property lets you customize how instances of your type will print to the console. Yep. We did that here, just a quick example right here. So we had this extension on the class asset, and this is saying we want it to conform to the custom string convertible protocol, and there's the description property as type string that's required by it. There are other common behaviors that you can unlock by conforming to standard library protocols. In this chapter, you will learn about 3 important protocols and the features that they offer your custom types. Okay. Equatable. Create a new playground called, okay. Let me do that first, brother. Stop task, yep. Save, sure. Playground. Harrison. Grab the. I'm gonna throw my mouse. Okay, there we go. Create a new playground called comparison to work in. The first feature you will examine is the ability to compare 2 instances of a type using the equality operator. I think there was, if I'm not mistaken, maybe it was the triple one. Oh, what's going on? All right. I think that's the type equality, and then this one is the value equality operator, maybe. Again, we're creating a new struct and 2 equal instances of it. Okay, import cocoa struct. So this is a value type. Struct point. Open up the body. Constant named x of type integer. Constant named y of type integer. And constant named try not to yawn. Okay. Constant named label of type optional string. And a default value of nil. Nil being synonymous with null. Null equal nil. Or sorry, null equal nil. Yeah, and then outside the scope of the type, so in the main body, let a, so another constant, and we assign it a value or an instance of point, and we pass in 3 for the x parameter, 4 for the y parameter, and then something similar for 3 and 4. Is that right? That's right. Okay. The struct above defines a point type. Points X and Y properties describe a location on a two-dimensional plane. Its label is an optional string that might tell the user what the point is used for. You know that these 2 points are equal. You created them in the same... Let me get the... There we go. Can't see if I... Okay. Just felt like it was crowding me, brother. Okay, so now... Its label is an optional string that might tell the user what the point is used for. Okay. You know that these 2 points are equal. You created them in the same XY with the same XY and label values. However, the point type does not know how to determine whether... Okay. My bad. Okay. The point type does not know how to determine whether one instance is equal to the other. Really? Oh, I probably have to give it explicitly give it a type. However, the point type does not know how to determine whether one instance is equal to the other. Try asking your program whether they are equal using the equality operator. Okay. Let A be equal. So this expression will just return true or false because of the operator. And then Command Shift Enter, run this bad boy. Bad boy. Oh, and it can't. Cannot be applied to 2-point operands. Okay. The check for equality does not work. In fact, it generates an error from the compiler. This error stems from the fact that you have not yet taught your point struct how to test for equality between 2 instances. To tell the compiler I intend to equate 2 instances of this type, you start by declaring that your type wants to conform to the equatable protocol. Well, I was in the ballpark. So this is in the same way that we can tell it, you know, for struct point. Well, wait. No, yeah, that's true. Yeah, so in the same way we would give it a type annotation, it's the same, it's written the same when we want to conform to a protocol, which protocols are types, so there's that. So now it's conforming to equatable. Okay, now what? Equatable. The errors are gone, and the results sidebar shows that your test for equality between A and B succeeds. Oh, so this will run now? True. All right. Too much are equal because they're X, Y. Oh, yeah. I mean, it seems like a Hadoi, but okay, so if I change it, now I get false. Fair enough. Try changing the X values so that they do not match. Okay, yeah. You should see that the 2 points are no longer equal. Make sure to change the values back before proceeding. Okay, they're back. Wait, is that really it? Mostly yes. Okay. You've already seen behavior that Swift implements on your behalf, such as the free initializers you learned about in chapter 17. Free initializers. Oh, right. Yeah, that just means, like when we do this here, right? Let A equal point. There's an instance. It's creating an instance of point. In here, when we write this, there's an implicit, what they call, can't even think, member-wise initializer, which just means that by default, it's creating this for you in it. want it to give me that autocomplete. There you go. Yeah, so it's doing that for you, so you don't have to write that. And it doesn't include the label because it's an optional, so it can be nil. You could add it, but that's why we don't have to have it here. And we can just pass in X and Y. But that's what member-wise initializers look like. It's just every property that you need for the given type is going to be a parameter of the same. All right, get rid of that there, fella. A, B. Okay. Free initializers. Swift and its compiler are doing work for you here as well. Cool. The equatable protocol has one requirement, an implementation of the equality function. You have not implemented this function for point, but just as the compiler can synthesize initializers, it can synthesize some other common function implementations. Implementation. Among them, the compiler can synthesize the equality operator for an equatable struct whose properties are also equatable. It will do the same for equatable enums whose raw values or associated values are equatable. It cannot synthesize equality operator for classes. Okay, the free implementation of the equality operator, which you are taking advantage of for point, checks the equality of every property on the two instances and returns true only if all properties are equal. Cool. You can also provide your own implementation of the equality operator. Do so now, making sure to add the function definition inside the points struct definition. Yeah, so if we want a function, we know we gotta, or if we want a method, which a method is a function defined inside of a given type. So a type's, any of the types available methods, any given type, the available methods are all functions, but they're functions that can only be accessed within the scope of that type. Okay, so static. Dang it, I forgot what static does. Hold on, it's gonna bother me. Static. Everything you've done so far with enumerations falls into the same general category, defining static cases. That's not what I wanted to. Okay, let's see. Trying to find where they define. Okay, for value types. Oh no, wait. Here, let's start here. In this chapter, you define some instance methods that were called on instances of a type. For example, terrorize town. It's an instance method you can call on instances of the monster type. You can additionally define methods that are called on the type itself. For example, is it an instance method of the monster type? Yeah. But you can additionally define methods that are called on the type itself. These are called type methods. Okay, well, either way, that's the answer. I mean, that's what they're called, type methods. But type methods are useful for working with type level information. For value types, you indicate that you are defining a type method. For value types, you indicate you're defining a type method with the static keyword. The method number of sides simply returns the number of sides a square can have. The static keyword tells the compiler that you do not want subclasses to provide their own version of make spooky no. Oh, okay, that's right. Yeah. Oh, so that is equivalent, because I've talked a little bit about final class, since it effectively it lets you use reference types, so classes, but without inheritance. So if you use final class when you define a class, it'll just restrict the creation of subclasses, thereby removing, inheritance from the equation, but still letting you use reference types if you don't want to copy everything. And so apparently final class, static keyword, they're functionally equivalent. Let me highlight that whole shebang. Actually, I should have just been doing this from the jump, but it'd be easier if I just put these on the board. So when we're done with the book, I'll share this. I'm gonna have to clean it up, but I'll make this board public and read only. That way, all of these conversations with ChatGPT are basically reasoning through some of the concepts of the book that I found more challenging. So yeah, I'll share these, but just FYI. But okay, so this is for static type methods in final class. All right. What is that beeping? It's fucking annoying. Oh, right, I came back here. I'm like, what the hell page am I on? Okay, so that's what that's doing. So this is just saying, don't let any other method or any other type provide a replacement implementation, because normally it works in a hierarchical fashion. So if it's required somewhere at a higher level, but then something lower that conforms to it or uses it, if it implements a method of the same name, it'll use the one specific to the nested type or the assigned type. But in this way, we can control if you wanted just a singular implementation of a certain thing to carry through to anything associated with this type. So that's what we're doing here. RHS, I don't know what that means, but let's see. Hold on, this girl. So send her a quick little message. She's in there jamming hard. All right. Okay. Where were we? Static func. Oh my gosh. Hold on, I'll be right back. All right, I was told to kick rocks, so here I am back. So, man. Okay. Where the hell was I? All right, so let's see. Get my butt positioning back. Dum-dum-dum-dum. All right. Let A be equal. We're back on this page. These two arguments of. Here. Operator implementations can be written either as global functions or as static methods on the types they operate on. The protocols cannot require global functions. Right. So the equatable protocol declares its requirements in the form of a static method. In the form of a static method. Okay. Oh, I'm a dummy. It didn't finish writing this. Point. Return arrow. So this should return a bool. True, false. Return keyword. LHS. LHS dot Y. Interesting. So you, and then you have to use these. You would have to use those. Oh no, those are the property names. Okay. Okay. Operator implementations can be written either as global functions or as static methods on the types they operate on. Protocols cannot require global functions. The operator function takes two arguments of type point called LHS and RHS. They represent the values that appear on the left-hand side and right-hand side of the operator when it is used. Oh. Left-hand side, right-hand side. I see. Okay, return left-hand side X equal to right-hand side X. Oh. All right. Then oh, okay, no, that's right. So LHS, oh, those are parameter names. Yeah, I'm tripping out. Okay, property names, XY label. Parameter names, LHS, RHS. And they accept points. Oh, so we would compare the whole thing. Okay. Gotcha. So we do pass it a whole point, and then internally it knows to return the comparison X, X, Y, Y, label. Okay. Yeah, all right. Your implementation returns true only if the X, Y, and label properties of both instances are all equal. This is identical to the implementation that the compiler previously synthesized for you. For a type that is not eligible for equatable synthesis, such as a class or struct with non-equatable properties, you must implement equality yourself, and sometimes you just do not want the free implementation. Sometimes you just do not want the, yeah. Suppose you do not care about points labels. In that case, two instances of point having equal values for X and Y would be enough for you to consider them equal and interchangeable. You would write your own implementation that only tests the values of X and Y. You have seen that organizing your code by implementing protocol conformance in an extension is common. Move your implementation of equality into an extension and update it to disregard the label. Bitch ass, maybe. Okay. So if I grab that there. What is X doing? I didn't realize that did something in Vim. All right, so can I visual select? Cut it. Get rid of the static. And extension on the point type, and we want to say it should conform to the equatable protocol. And now we paste our dilly, static func, LHS, RHS, and get rid of that there. Static func. Return. Right hand side X and left hand side Y equatable to RHSY. Redundant conformance of point. Wait, does that? Oh, we took it off there. Okay. Extension. Okay. Where am I? GG. Or 0 or shift dollar to get to the end. Get rid of it here. And I want to go to 14. Ah, shit. Yeah. Okay, your instances are still equal, and point is now a well-organized equatable type. Okay, so we define the type itself, and then further down the way we write an extension for that same type, in this case point. So we extension point. We say it now should conform to the protocol equatable, and since it is an extension on the point type, that means that the point type itself inherits from the extension. And then we implement the operator static because we don't want anything else to redefine it. And so this is what it'll be. So it'll take these two parameters of point type, it'll return a true or false, and this is the implementation. So anything we use needs to have properties of X and Y, but we know that it will because it's of type point. Okay. In fixed operators, it may feel strange to declare equality as a static method. In chapter 15, you learned that static methods are defined on a type. But you do not call this method on the point type, like point. Yeah. Indeed, operators like equality are declared at the global level in Swift. The global or the equality operator is declared like this in the Swift standard library. Precedence group, comparison precedence. Higher than logical conjunction precedence. But the infix operator, equality of type, comparison precedence. Do not worry about what a precedence group is right now. That is discussed in the section called For the More Curious Custom Operators at the end of this chapter. But do note that the equality operator is declared as an infix operator. This means that its implementation is executed by placing the operator between the two instances it will operate on. Is executed by placing the operator between the two instances. Okay. Hence, you called points implementation of equatable via this code in the example above. Okay. The Swift compiler knows to check both in the global scope and inside types for implementations of operators. Placing them inside types as static methods is the more stylish approach. Okay. Buy one method, get another free. Your point struct now conforms to equatable, so you can test points for equality. As it turns out, you can check for inequality too. Try it out. All right. Let a be not equal a b. Oh, that's is not. So A is not equal to B, and that's false. Okay. As the result sidebar shows, the test for inequality yields false because the points are in fact equal. So a standard library provides a default implementation of the does not equal function via an extension to the equatable protocol. This default implementation uses the definition of equatable and negates the result. So if your type conforms to equatable, then it also has a working implementation of the does not equal function, whether it uses the default implementation of equatable or its own version. Oh, I see. Oh, okay, yeah, so and it'll always just negate it. Cool. All right. So comparable. Now that your point type conforms to the equatable protocol, you may be interested in more nuanced forms of comparison. For example, perhaps you want to know if one point is less than another point. As with equality, types must define for themselves what it means for one instance to be less than another. You define this functionality by conforming to the comparable protocol. Start by reviewing the documentation for comparable. You have not typed it anywhere yet, so you cannot option click its name. Instead, open Xcode's help menu and select developer documentation. Search the documentation for comparable and select the result for the comparable protocol in the Swift standard library. Under conforming to the comparable protocol, you will find that you need to implement the infix operator as well as the equality operator. Update the extension on your struct to make it conform to comparable. Okay. Developer docs. And select the result for the comparable protocol. Look at all this stuff. It's crazy. Protocols. Special use strings and text collections, basic international programming task, distributed actors. Where the hell are they? Okay, well, let's just do Objective-C runtime. There we go. The comparable protocol is used for types that have an inherent order, such as numbers and strings. Many types in the standard library already conform to the comparable protocol. Add comparable conformance to your own custom types when you want to be able to compare instances using relational operators or use standard library methods that are designed for comparable types. The most familiar use of relational operators is to compare numbers, as in the following example. Okay, conforming to the protocol. Types with comparable conformance implement the less than operator, the equal to operator. These two operations impose a strict total order on the values of a type. Okay. A equal to B, A less than B, B less than A. Here's I'm going to define the less than and equal operator as static methods of your types. Because default implementations of the remainder date structure, struct date, year, month. To add conformance, first declare the conformance to comparable and implement the less than. So extension on date, we have to say it conforms, make it a static function, less than, okay. Function uses the least specific. This function uses the least specific non-matching property of the date to determine the result of the comparison. For example, if the 2-year properties are equal but the 2-month properties are not, the date with the lesser value for month is the lesser of the two dates. Oh, okay. Next, implement the static func return. Okay. Update the extension on your struct to make it conform to comparable. Static func. Extension. Static func LH. Oh, in addition to this one. So that's for, yeah, that there. Static func. Less than, left-hand side. Type point. Right hand side, point, bowl, return, LHS X, less than RHS X, and left hand side Y less than right hand side Y. Your implementation of the less than function works similarly to your implementation of the equality function. Checks whether the point passed in on the left hand side is less than the point passed in on the right hand side. If the x and y values for the point on the left hand side are both smaller than the values on the right hand side, the function will return true. Otherwise, function will return false, indicating that the point on the left hand side is not less than the right hand side. Create 2 new points to test this function. Okay. Let's see, equal point, point x 2 y 6, let d equal point 3 and 7, let cd equal, and that should be false. C is not equal to D, and then C less than D. C. False for C and D. Oh yeah, that makes sense. C is less than D. Okay, so this is important. Your implementation of the less than function works similarly to your implementation of the equality function. It checks whether the point passed in on the left-hand side is less than the point passed in on the right-hand side. If the x and y values for the point on the left-hand side are both smaller than the values on the right-hand side, the function will return true. Okay, so all properties, basically. So it's all or nothing. Okay. Otherwise, the function will return false, indicating that the point on the left-hand side is not less than the right-hand side. Okay. Wait, so C is less than D, that's true. C, because 2 is less than 3, 6 less than 7. But if I make that 8, okay, yeah, so it is all or nothing. Now it's back to true. Okay. So the condition must apply to all properties, effectively. As with implementing equality to conform to equatable, implementing less than to conform to comparable gives you bonus functionality. The Swift standard library defines the greater than or equal to and less than or equal to operators in terms of the less than and equality operators. This is why comparable only requires you to overload the less than and equality operators. If your type conforms to comparable, then it will get implementations of the other operators for free. Note that, unlike for equality and equatable, the compiler cannot synthesize the required less than function for you. You must provide your own implementation, carefully considering what it means for your program for one instance to be less than the other. Interesting, brother. Yeah. Okay. Yeah. Should it mean that all properties are less or something else? Right, you could treat it. That's cool that you can control that. Okay, so you could. Some people might view it as, 2 plus 6. Is that less than 3 plus 7? Kind of a thing. But that would, well, it wouldn't make sense for points, but, or at least for graphing, but that could make sense in a lot of other ways. Huh, I'll have to think about that. Note for, properties, okay. For example, should it mean that one point is closer to the origin 0, 0 than the other? Your implementation should reflect your decision. Test your free functionality by adding a series of new comparisons. C less than D. Let C less than equal D equal C less than or equal to I don't need the spaces, right? Yeah, let C greater than D C Wait, binary operator. Less than or equal to D. Maybe this is one of those intentional errors again, but I don't think so. Let greater C greater than equal D. And cannot be applied to 2-point What? Why am I getting errors here? Maybe I need the spaces, I don't know. Doesn't matter, okay. What's the problem? Okay, I definitely missed something. Comparisons, comparable, conforming to comparable. Oh, I did miss that part. Extension point, equatable, and comparable. So these are both conforming now. I think that's all I missed, yeah. Okay. So if we run this now, do we get the same? It's not running. Come on, dude. Run it. There we go. True, false, false. Would you get true, false, false? Yep. Okay. And that's saying C less than or equal to D. So that would be true. Makes sense. C greater than D. C greater than or equal to D. Also false. Okay. As anticipated, these comparisons evaluate to true, false, and false respectively. You can also make a range of any comparable type. Add this to your playground. As these compare by true. You can also make a range of any comparable type. What does that mean? Let point range equals C. Oh, cool. C up until whatever's less than D. Nice, brother. Point range contains A, and A is 3, 4. Oh, okay. Point range contains point Y. This is pretty cool. X2, 6, 3, and 7. Y up till I would have thought less than would have been 2 and 6, not down. I wonder if they list that regardless of the operator, probably, because that seems obvious. Okay. Let's see. That point. Here you define a range of points and then check whether two specific points exist within that range. How does this work? Swift does not need to compute all possible values that would fall within a range. An instance of range only stores the lower bound and the upper bound. When you ask a range if it contains a value, the range compares to the value to its bounds. Swift does not compute all possible values. An instance of range only stores the lower bound and the upper bound. When you ask a range if it contains a value, the range compares the value to its bounds. Okay. With the exact comparison depending on its type. A half-open range like this one returns true if the value is greater than or equal to the lower bound and less than the upper bound. Okay. Yeah, so it is. Okay. Since conforming to comparable means that you have defined what it means for one point to be less than another, this check can be performed. Okay. Meaning we defined equality and whatever less than is. Protocol inheritance. Comparable inherits from equatable. You may be able to guess the implication of this inheritance. To conform to the comparable protocol, you must also conform to the equatable protocol, including, as you have seen, by supplying an implementation of the equality operator. This relationship also means that a type does not have to explicitly declare conformance to equatable. Oh, okay. If it declares conformance to comparable. I see. So this is the same. Nice. Okay. A note on style. While it is not wrong to explicitly declare conformance to both equatable and comparable, it is unnecessary. If your type conforms to comparable, then it must conform to equatable as well. This point is a detail listed in the docs, which makes it an which makes it an expected consequence of conforming to comparable. Adding the explicit conformance to equatable does not really add any information. I call bullshit because that's making a big assumption that people actually read documentation. And I can tell you, most of them don't. The vast majority. On the other hand, it may make sense to have a type explicitly conform to all protocols involved when conforming to a custom protocol that inherits from another protocol. Although it is still unnecessary, it may make your code more readable and easier to maintain because your custom protocol is not listed in the official documentation. Hashable. When you learned about the dictionary and set types in Chapter 10 and Chapter 11, you learned that in order for a type to be included in a set or used as the key type in a dictionary, it must be hashable. A type is hashable when it conforms to the hashable protocol. Hashability has a straightforward purpose: the ability of a type to generate an integer based on its content. The ability to, that's a, that's a block for sure. Hashable. Okay. Close that bad boy, and then a type is hashable when it conforms to the hashable protocol. Hashability has a straightforward purpose: the ability of a type to generate an integer. The ability of a type to generate an integer based on its content. Oh, okay, okay. I see. Neat. But why is that useful? Encoding or decoding. Yeah. Any kind of coding or mapping. Yeah, hashing is you see it everywhere. Put some point instances to work in a set and dictionary to see the error that you get. Put some in a set and a dictionary. Okay. Beneath the neg. Okay, right here. Let points. So constant variable of type set, and it's equal to this set. Points. Points. Intersection. B. C, D. And then let point names be of type, or what is this here? It's an array of what is this? Point string? Is that a set? Equal. I don't recall these all that much. You learned about in chapter, you learned that in order for a type to be included in a set or used as the key type in a dictionary, it must be hashable. Okay, I guess it'll tell me. Which string is equal to point xy 0 0 origin a what? So this, what the hell is this? Here you define a set of point. Okay, so that's a set. Oh, the dictionaries had names. That's right. Okay. So that's a set. Here you define a set of point instances and call its intersection method. You also create a dictionary whose keys are points and use it to give names to some points. The compiler emits two errors. Generic struct set requires that the point conform to hashable, and type point does not conform to protocol hashable. That is straightforward enough. You must make point conform to hashable for either of these uses of the type to be legal. Okay. Similar to equatable, the compiler will happily synthesize implementations of hashable's requirements for structs with all hashable stored properties, and enums requirements for structs and with all hashable stored properties, and enums with no associated values or all hashable associated values. Update point to conform to hashable. Comparable and hashable. Okay. Because point is hashable now, the compiler can understand all these uses of point. Okay. So these are sets. This is a dictionary. Gotcha. So we're saying of type dictionary, two values on the left, type point on the right, type string. There's the point and the string. And that's origin, and then A. What's A? Point A. Oh, which is 3. Okay. Huh. Custom hashing. Unfortunately, the free implementation that the compiler has synthesized for point is problematic. To understand why, you need to learn a little bit about hashes. In Swift, the hash of an instance is an integer that is generated from the instance's data. Comparing the hashes of two instances of a type can be a very fast way to check whether the instances are different, often much faster than comparing the instances using the equality operator. Consider how long it would take to compare two instances of string for equality. The program must advance along the complete length of at least one of the strings, comparing the character at each index to the character at the same index of the other string. If the program gets to the very end of the strings without encountering a difference, the strings are the same. By contrast, comparing two integers is blazing fast, and modern CPUs are often designed to make it even faster. If you want to know whether two strings are equal, you can first check their hashes, which takes nearly no time at all. If their hashes are different, then you know the strings are different. Okay, that makes sense. Actually, this too shall be saved. Give that block, brother. And custom hazing, hashing. Okay. But because strings can be larger and more complex than integers, it is possible for two different strings that have the same hash. So if two strings hashes are the same, you have not learned anything. Oh, look at that. Oh. Stretch it out, brother. All right, now. Yeah, equality check to be sure. As an aside, because an equality check is a necessary backup plan when comparing the hashes of instances, hashable inherits from equatable. Okay. An ideal hashing algorithm is one that is fast to compute and unlikely to collide with another instance's hash, but does not need to guarantee that two hashes will never be the same. To make lookups and comparisons as fast as possible, dictionaries use hashes as an initial check to ensure that dictionary keys are unique, and sets use hashes as an initial check to ensure the uniqueness of their contents. Adding lots of instances with the same hash value would force these types to fall back on equality checks to ensure uniqueness, which can be much slower. Fortunately, Swift has a safe, fast hashing algorithm built in. All you have to do is tell Swift which properties of an instance should participate in the computation of its hash. Swift calls these properties that contribute to an equality comparison the instance's essential components. Yeah. That is great. And maybe belongs on the board too. Let's see. Hashable here. Your current implementation of the equality operator uses only the x and y properties of a point. However, the compiler synthesized hash of a point uses all the instances stored properties, and that is the source of the problem. If one property is not relevant to an instance's uniqueness, then it should not be an essential component for hashing. To control which properties of an instance will contribute to its hash, you must provide your own implementation of the hashable requirement. That requirement is an implementation of a method called hash. Implement it in your point extension. Okay. Func hash into hasher. And this keyword being if we wanted, I think if we have to write this if we are changing the input. So whatever we pass into the hasher parameter, if we want to transform that value, we have to notate it with that in out. It's like if you let your user, type in some code and it interprets that, does something for them. Something along those lines, and then returns that value, which my app probably will do, at least in a few places. Yeah, some of the sandboxing environments, what if type scenarios. Yeah, so we'll be using that hasher combine x hasher combine y. Okay. When Swift needs to compute your object's hash, it will call hash into and pass in a reference to an instance of the hasher struct as its argument. Swift needs to compute your object hash. hasher implements Swift's hashing algorithm, and your job is to tell which properties to include by passing them to its combine method. That is all. Point is now stylishly hashable. And pass in a reference to an instance of the hasher struct. Okay. Combine. And we leave out label. Okay. Okay. For the more curious, custom operators. Swift allows developers to create custom operators. This feature means that you can create your own operator to signify, for example, that one instance of the person type has married another instance. Say, for example, you want to create a plus function to marry one instance to another. Create a new person class like so. Class person. Hold on one second. Okay, class person. Mutable variable. Named name of type string. We want this variable to not add to the reference count when in use, so weak var is required, or the keyword weak is required, spouse, and it's of type optional person. Okay. And we want it to have a custom initializer, so we init name will initialize with the name parameter and the spouse parameter. And whatever we pass in will be the instances, very same properties, self.spouse. Okay. A class has two properties, one for name, another for spouse. It also has initializers that will give you values to those properties. Note that the spouse property is an optional to indicate that a person may not have a spouse. Next, create two instances of this class. Okay, let Matt equal person name spouse. So just two unmarried brothers right here. Let Drew person name. Oops, name is Drew. Spouse also Neil. Now declare your new infix operator. It has to be declared at global scope. Also, define how the new operator function will work. Weird. Infix operator plus func. Left hand side. Oops. Person right hand side person, left hand side spouse, RHS, right hand side spouse. Okay, the new operator will be used to marry two instances of the person class. So it'll take left hand side person, right hand side person, and then set left hand side LHS spouse to equal the right hand side. Oh, okay. So the instance on the left set that spouse value to the value on the right hand side. So we could do oh, okay, I see. So we would do like and some lady. Does that work? Not a urinary what? Or maybe you can't call it like that? Why didn't it work? Will be used to marry two instances of the person class as an infix operator. Oh, I gotta call. Okay, my bad. As an infix operator, it will be used between two instances. Oh, I see. So Matt plus Drew. Did it work? So what does higher than refer to in the code above? No idea. Higher than defines the priority of the operator's relative relationship to another precedence group. In this case, default precedence has a priority that is higher than ternary precedence, which is, this is the precedence group for the ternary operator. See chapter 3 for a discussion on the ternary operator. That means your new operator, plus plus plus, will have a higher priority than the subtraction and will be executed before the subtraction. Wait, what? Oh, that's just a dash. Will have a higher priority than and will be executed before the ternary operator. Okay. Think of how multiplication has higher priority than addition in expressions like 4 plus 3 times 3 minus 1. Yeah, because multiplication has a higher priority. Yeah, so what, 9? 4 plus 9 minus 1. 4 plus 9. 13 minus 1, 12. Okay. If addition had higher priority than multiplication, then the answer would be 20. Yeah, and it's weird how that works. Precedence groups offer a number of other options to define the custom operator in addition to higher than. Another important option that you will often see is associativity. Associativity. Yeah. Associativity defines how operations of the same priority group together. Associativity defines how operations of the same priority group together. Okay. It takes one of two values, left or right. For example, the operators plus and minus both use the same precedence group, addition precedence, and therefore have the same priority. Both are also left associative. The associativity and precedence for the mathematical operators mean that the order of execution in the equation above is, what we learned in high school. That is 3 times 3 is evaluated first because it has the highest priority and its product associates to the left. That yields 4 plus 9 minus 1, which is 12. Because plus 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 is intended to marry two person instances together, it does not need to be chained together with multiple calls. For example, you would not see this code, Matt plus 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 Drew plus plus plus. I mean, I just got to say it. Why is it 2 guy names? You know? Anyway, it does not need to be chained together with multiple calls. For example, you would not see this code Matt, Drew, some other instance. Thus, you can take advantage of the default values for precedence and associativity. Whoops. Where do we go? Thus, you can take advantage of the default values for precedence and associativity. How about this? In your face, fucking agenda, Maddie. How about that? You like that? Maddie. Now it's a girl. Nice try. Fucking around. Thus, you can take advantage of the default value. Okay. Get rid of that there. Of the default values for precedence and associativity. Exercise your new operator. All right. Let's go downtown Charlie Brown. Here. Maddie, a woman, marries Drew, a man. And Maddie. Not you too, big nerd. They got you too, brother. All woke shit. Come on. Can't even keep it hetero in a book. Spouse, name. What do we get? Maddie.spouse. It might be nil, so we have the question mark optional chaining .name, and that is Drew because we just married the two. Gotcha. Cool. Yeah, that's cool. You could just write a function though. I mean, oh, but you know what? This would be great for like a DSL for sure. Yeah, that's pretty cool. Okay, the code Matt plus Maddie plus Drew. Serves to marry the two instances. Check that this process worked by examining the playground's results sidebar. While this operator works, it's not too difficult to determine what is going on by looking at it. We generally recommend that you avoid declaring custom operators. Exactly. It's good practice to only create custom operators for your own types when the operator will be recognizable to anyone who may read your code. Which is nobody. You know, until they get trained for 6 months and then leave in a year, and then you got to train, you know, another person. And so, yeah, I would recommend not writing custom or DSLs internally. Learn that the hard way. But let's see. Then again, it can be a good way to have some very tight job security and establish leverage for raises and whatnot. So actually, it really ended up helping way more than it hurt. But yeah, so maybe you should do it. While this operator works and it is not too difficult to determine what is going on by looking at it, we generally recommend... Oh, we read that. In fact, Swift only allows you to use well-defined collection of mathematical symbols to create custom operators. For example, you cannot rename the +++ operator to be the emoji face throwing a kiss. Why? Someone reviewing your code in the future may not know exactly what you meant by +++. You might even forget yourself. Moreover, it is not as though this custom operator is more elegant or efficient than a marry method would be. Yeah, exactly. Lame, they don't let you do it though. Why restrict it or why even... That was one of the things I read about Swift was the full support for Unicode, but you can still use like a let something equal a poop. Just gotta put it in a string, and then it should let you. Yeah, so then it's a variable. That's hilarious. Oh man. Okay. But we just can't use this as a addition symbol or some kind of operator. Property wrappers. Okay. I have to use the restroom, and it's a good stopping point. It was a short one today, but we'll be back tomorrow to start on this new chapter here. So thanks everyone for tuning in. Make sure you drop a follow, drop a sub, drop a nub, and check me out at 9 p.m. Central Time on this same channel for 100 Days of Halo day 65, something like that, tonight.